So in the last video, I wrote my own database from scratch and I explained how all the algorithms and data structures work, but apparently the amount of stuff that you can explain in a 42-minute long video after you've been coding for 7 months straight is kinda limited. So in this video, we're going to dive deeper into one of the sorting algorithms used by databases to sort giant tables when they do not fit in RAM. First of all, I'm going to give you a quick introduction to the problem we're trying to solve here so that you don't have to watch 42 minutes of database lore, essentially. Although you probably should. So one of the things I learned after having written a database is that databases can never assume that a table fits in memory, because any table could potentially contain hundreds of millions of rows, which could amount to many gigabytes in size. So if your system's available memory is 4 gigabytes and you have a table that's 8 gigabytes in size, you cannot load the entire table into memory. Imagine this is a books table and each book has a title and a description. And now let's say the database receives a query that needs to order all the books by title and retrieve the first 100 results. How is the database going to sort all the books? Because it can't just call .sort on some array in memory. It's nowhere near that simple. It has to sort on disk. Well, there are a few algorithms that you can use for this, but I'm going to explain to you the algorithm that I implemented in my database, which is the K-way external merge sort algorithm. Before we start explaining how this algorithm works, there are a couple of things you need to know. The first one is a little bit of terminology. So in database terms, rows are called tuples. This term comes from relational algebra, which is the math behind databases, and after writing so much database code, I just got used to calling rows tuples, so that's how I'm gonna call them. The second thing you need to know is that database tables are stored in a file on disk. This is just a normal file, like any other, it's not magic, although it does have a very intricate binary format due to the storage data structures used by databases, which are very complex. And so this particular file cannot be used for sorting, because you need a format that's more adequate for sorting, and on the other hand, you can't just alter the contents of the table file every single time you receive a query that wants to sort something. That doesn't make any sense, right? So this is what a database does when it has to process queries that need to sort the results. The database allocates a fixed size in-memory buffer and it starts loading tuples or rows from disk into the buffer. If all the necessary tuples fit in memory, for example if the table is only a few megabytes in size, then in that case you can actually call .sort on the buffer and that's it, you're done. You've sorted the entire table. But if you have to load more tuples than the buffer can fit, then the database dumps the memory buffer to a temporary file and it loads more tuples into the buffer again until it's full. Then it appends the results to the temporary file. And it keeps doing that until it collects all the tuples into a temporary file with a format prepared for sorting. So now that you understand all the context, we can finally explain how the external merge sort algorithm works. The starting point is we have a file that contains many unsorted tuples, and we're gonna do a certain number of passes through the file until we sort all of them. But before that, we need to do some preparation for the algorithm. The first step is dividing the file into fixed size pages. Each page is basically a unit that contains a number of tuples. For simplicity, let's say each tuple is 20 bytes in length and each page contains 3 tuples, which means each page is 60 bytes in length. Now that we know the size of the data we're working with, we need a way to load and process pages in memory. And for that, we're gonna use k input buffers and 1 output buffer. Each buffer will be able to store one entire page at a time. So we need 60 bytes for each buffer in this example. And the reason this algorithm is called K-way is because we can have k input buffers. The number of input buffers impacts how fast we can actually sort. But again, for simplicity, let's just say we have 2 input buffers, k equals 2. So this is going to be a 2-way external merge sort. Alright, the first step is pass 0. In pass 0, we're gonna load sequences of k pages in memory and sort them. Since k equals 2, we start by loading the first 2 pages into the 2 input buffers that we have available, and then we sort each input buffer individually in memory. Once that's done, we have to merge the pages. So we compare the first tuples in each input buffer and we move the smaller tuple to the output buffer. And now we keep doing that until the output buffer is full. Then we write the output page back to the file and we continue the process of merging until there are no more input tuples. At that point, the output buffer will be full again and we'll write the next page to the file. So with this, we've produced a sequence of 2 pages that are fully sorted from start to end. This is called a 2-page run. Now we basically repeat this little algorithm for the rest of pages in the file. We still have 3 pages left, so we load the next 2, we sort each buffer individually, we start merging tuples, moving them to the output buffer until the output buffer is full, and then we write the output page back to the file. When this run completes, we'll have produced another sequence of 2 pages that are fully sorted from start to end. Now for the last page, since there's only 1 instead of 2, we don't even have to merge anything. We just load it into memory, sort it, and since there are no comparisons to be made, everything moves to the output buffer and we write the page back to the file. And so pass 0 is now fully completed. The file has been successfully divided into sequences of 2-page runs, or in other words, 2 sorted pages. But that doesn't mean that the entire file is sorted, so we still need more passes. Now we move to pass 1, and this is where the real algorithm begins. Everybody gets that you gotta do pass 1. For each run in this pass, so we got a loop, each input buffer will process an entire 2-page run from the previous pass in order to produce a 4-page run. Therefore, we need to set up a couple of cursors. For the first run in this pass, the first input buffer will work with pages 0 and 1, while the second input buffer will work with pages 2 and 3. Once we have the cursors positioned, we load the corresponding pages into each input buffer, we shift the cursors so that they point to the next page, and now we are ready to merge the pages in memory. From now on, we don't actually have to sort anything anymore, we just merge. If you ever had to implement the normal in-memory merge sort algorithm, you know that merge sort doesn't actually sort anything, it just merges stuff. So if you've ever done that, you can kind of start to see where this is going. But anyway, we merge the smaller tuples just like we did before until we fill the output buffer. And now we're going to introduce a little change to the algorithm, which is that we're going to write output pages to an output file. So we're going to have 2 files. We're going to have an input file where we read pages from, and we're going to have an output file where we write pages to. And the reason for that is that since each input buffer works with multiple pages, we don't want to be overwriting pages that we haven't loaded into memory yet. You'll see in a moment exactly what I mean by this. Now we continue the process of merging by moving the smaller tuple to the output buffer, and this time when one of the input buffers empties, we have to load the next page before doing anything else, otherwise the run will not be correct. Once the page is loaded into memory, we can continue with the comparisons and fill the output buffer. Then we write the next page to the output file, and now you can actually see why we need a separate file. It's because if we were to use the same file, we would have overwritten the second page, page number 1, which we haven't loaded into memory yet, so we can't do that. And now it's just a matter of doing the same thing over and over again. So keep comparing and moving tuples, load the next page when an input buffer empties, compare and fill the output buffer, write the next page, and keep doing that until there are no more input tuples. So as you can see, using a couple of 2-page runs from the previous pass, we've produced a 4-page run in the current pass. So a sequence of 4 pages that are fully sorted from start to end. And so now we will just have to do the same thing for as many pages as we have in the file. In this case, there's only 1 more page left because the available space on screen is kinda limited, but you get the idea. If we had more 2-page runs that we would have processed in the previous pass, we would just shift the cursors and produce as many 4-page runs as we can. In this case, since we only have 1 page left, we load it into memory, no comparisons, so move everything to the output buffer and write the disk. If you have successfully understood pass 1, then you understand the entire external merge sort algorithm. But I know it's complicated, so let's do pass 2, because the file is still not fully sorted because of that last page, so we need an additional pass. In this pass, we're gonna swap the files so that the previous output file becomes the new input file and vice versa. That way, we only need 2 files for the entire duration of the algorithm. And just like before, for each run in this pass, each input buffer will take an entire 4-page run from the previous pass and will merge all that into an 8-page run. For the first run in this pass, the first input buffer will process pages 0, 1, 2, and 3, while the second input buffer would process pages 4, 5, 6, and 7, but we only have page 4 in this example. So again, set up a couple of cursors, load the first pages into memory, shift the cursors, the second one is already at the end, and now merge. Due to the current order of the tuples, nothing interesting is going to happen until we load page number 3, because pages 0, 1, and 2, they all have tuples that are less than 10. So the comparisons will always pick tuples from the first input buffer and write them to the output file. So we'll just load page number 1, move it to the output buffer, write it back, load page number 2, move it to the output buffer, and write it back. Once we reach page number 3, however, the comparisons will start to actually do something, because now you can see that we need to move tuples from both buffers, just like we did before. So we write the output page, we do the rest of comparisons, and we write the last page. And now we're done. This was supposed to be an 8-page run, but we don't have 8 pages to begin with. The thing is, if we had more 4-page runs that we would have processed in the previous pass, we would just move the cursors to the necessary locations and produce as many 8-page runs as possible. And in the next pass, we would do 16-page runs. The pass after that would do 32-page runs, and so on. The algorithm scales logarithmically, because it keeps multiplying by k. The greater k is, the less passes you have to do through the file, which is important because it reduces I/O. Everything works exactly the same with more input buffers. If you had 10 input buffers, so k equals 10, instead of loading 2 pages at a time, you just load 10 pages at a time. And you do all the comparisons with 10 pages, you have to search for the minimum tuple in a for loop, but other than that is the same thing. And this is interesting because let's say we need to sort 1,000 pages. Using only 2 input buffers, we would need 10 passes in total. However, if we use 10 input buffers, we would need only 3 passes, because pass 0 does 10 page runs, pass 1 does 100 page runs, and pass 2 does 1,000 page runs, because it multiplies by k. The downside is that we're using more RAM because we need more buffers. And there's another detail here, which is that you have to deal with variable length data, because not all the rows are the same size. If you've seen the previous video, you know that variable length data complicates everything. And in this case, imagine you have a couple pages in the input buffers, pages are 60 bytes, and you have tuple 1 of size 40 bytes, tuple 2 of size 60 bytes, and T3 of size 20 bytes. Now when you merge, you realize that you cannot fit T1 and T2 in the same page. So you have to produce a page that contains only T1. And then you have to produce another page that contains only T2 because T3 is not gonna fit. And after that you produce another page that contains only T3. So using only 2 pages, you've produced 3 pages, which means that due to fragmentation, you don't know how many pages each run is going to produce. And the reason you need to know that is because that's how you compute the positions of each cursor in the next pass. So unfortunately, I didn't find any simple solution for this. I did find some papers that address this issue, but I just came up with my own trivial, naive solution, I guess, which is basically storing in a queue on disk how many pages were produced in all the previous runs, and then using that to compute the cursor positions. Now, this may not be the most efficient way of dealing with this problem, but it works. So that's my implementation of this algorithm, probably the worst out there, but this algorithm can be implemented either recursively or iteratively, and the number of input buffers can be generalized using for loops. So if you're interested in the source code or you want to get into the details, it's on GitHub, it's linked in the description, and the next time you ask a database to sort something for you, you should at least probably give it some props, because this is no easy feat. So yeah, that's it for this video. See you in the next one.